In this video, we will learn more about raster data. Raster data is made up of pixels or cells, and each pixel has an associated value. In its simplest form, a raster consists of a matrix of cells organized into rows and columns, or a grid. As shown in the graphic, where each cell contains a value representing information such as temperature. Rasters can be digital aerial photographs, imagery from satellites, digital pictures, or even scanned maps. In GIS, the pixel values may represent elevation above sea level or chemical concentrations, rainfall, etc. The difference between a digital elevation model, or DEM, in GIS and a digital photograph is that the DEM includes additional information describing where the edges of the image are located in the real world, along with how big each cell is on the ground. This means that your GIS can position these images, DEMs, hillshades, slope maps, correctly relative to one another, allowing you to easily build up the layers of your map. Cell values can be either positive or negative, integer or floating point. Integer values are best used to represent categorical or discrete data, and a floating point is best to represent continuous surfaces. Cells can also have a no data value to represent the absence of data. A cell value applies to the center point of the cell and to the entire area of the cell as well. The dimension of the cells can be as large or as small as needed to represent the surface conveyed by the raster dataset and the features within the surface, such as a square kilometer, square foot, or even a square centimeter. The cell size determines how coarse or fine the patterns or features in the raster will appear. The smaller the cell size, the smoother or more detailed the raster will be. However, the greater the number of cells, the longer it will take to process, and it will increase the demand for storage space. If a cell size is too large, information may be lost or subtle patterns may be obscured. For example, if the cell size is larger than the width of a road, the road may not exist within a raster dataset. In this diagram, you see how a simple polygon feature would be represented by a raster dataset at various cell sizes. Raster datasets that contain attribute tables typically have cell values that represent or define a class, group, category, or membership. When a raster attribute table is generated, there are three default fields created in the table: an OID, a value, and a count. It is not possible to edit the content in these fields. The object ID, or OID, is a unique system-defined object identifier number for each row in the table. Value is a list of each unique cell value in the raster dataset, and count represents the number of cells in the raster dataset with the cell value in the value column. Cell values represented by no data are not calculated in the raster attribute table. Data stored in a raster format represent real-world phenomena such as thematic data, also known as discrete data, which represents features such as land use or soil types, continuous data representing phenomenon such as temperature and elevation data or spectral data, including, for example, satellite images and aerial photographs, and pictures such as scanned maps or drawings and building photographs. Raster data is exceptionally useful for a wide range of applications. Rasters can be base maps. For example, ortho photographs displayed underneath other layers provide a map user with confidence that map layers are spatially aligned and represent real objects. As shown in the image, three main sources of raster base maps are ortho photographs. You can have aerial photography, satellite imagery, and scan maps. Rasters are well suited for representing data that changes continuously across a landscape or surface. They provide an effective method for storing the continuity as a surface. They also provide a regularly spaced representation of surfaces. Elevation values measured from the Earth's surface are the most common application of surface maps. Other values such as rainfall, temperature, concentration, and population density can also define surfaces that can be spatially analyzed. Rasters representing thematic data can be derived from analyzing other data. A common analysis application is the classification of a satellite image by land cover categories. Basically, this activity groups the values of multispectral data into classes, such as biophysical settings, and assigns a categorical value. Thematic maps can also result from geoprocessing operations that combine data from various sources, such as vector, raster, and terrain data. Rasters used as attributes of a feature may be digital photographs, scanned documents, or scanned drawings related to a geographic object or location. The question often arises, which one is better? The answer is neither and both. Neither of the two classes is better in all conditions for all types of data. Both have advantages and disadvantages relative to each other. In many cases, you can represent the same data in vector and raster formats. It is even possible to convert data from one model to another. This allows you to take advantage of the strengths of both data models. Creating a grid from polygons involves conceptually overlaying the grid cells with the vector data and assigning the cell a value based on the polygons contained in that cell. Creating polygons from a grid is relatively simple. Just follow the boundaries between the different cell values. Obviously, some accuracy is lost with either conversion method.